go back here. So what we do here, if we go back to what we have in the Gaussian-Seidel map versus the matrix format, let's go back to take a look. And so we review something and then learn the new things. And this is the Gaussian-Seidel map version. And we have the AX. So how can we get this matrix format? And then actually you can get it by writing the left-hand side by D plus L plus U. That is the AX, right? And then putting the X here, and then equals to the B. And this is AX equals to B. But now you move the U to the right-hand side, and then you have the D plus LX, and then equals to the B, and then, am I right here? Minus UX. There's something wrong here, I guess. Am I right for the U matrix? Let me get something wrong with my L matrix here. Oh, there's a minus side there. I forgot it. This one should be the minus side. This is the Gauss-Seidel method. There's a typo here. Because on the right-hand side, you will see that this is the green part, and then the green part has the minus sign. I forgot the minus sign here last time. So this one is correct version, and then we switch the A matrix into the L, D plus L plus U, and then we move the U to the right-hand side, and then we let the left-hand side to be the K plus 1, and then we let the right-hand side to be the K. Or the K here, or the K minus 1 here, and then so for the K XK, and that's how we get the get to the. So both sides we multiply the inverse and then B, and then minus the D plus L, and then inverse U, and then XK minus 1. And this is one method to get the matrix format for the Gaussian-Seidel methods as well. This is the same format as this one, but I just explained the idea again by approaching this format by another method, by splitting, decompose the A into D plus L plus U, and then move the things around, and then let the things on the left to be the K iteration, and then to let the things on the right to be the K minus 1 iterations result. And this is how we get the matrix format. So now let's go back to the SOR. It's quite similar, but we are splitting the A and then L, and then A equals to D plus L plus U. And now we are splitting the D, splitting the diagonal matrix with a weight parameter, parameter W. Oh, it's omega here, parameter omega. And which means that I'm going to let the D to equals to 1 omega D, and then minus 1 omega divided by omega D. And if you do the subtractions, and then you will find out that this is 1 over omega minus 1 over omega, and then that is just 0. And then minus, this is a subtraction sign here, omega divided omega, and then it's just a D. So you can see this is just a D diagonal matrix. And now let's do the things again. So as you can see before, I lift the D matrix on the left-hand side and plus UL on the left-hand side. So at the very beginning, this is the AX equals to B problem. So I go from the very top, and then I split the things into L plus U, and then X, and then B B vector on the right. And then now I'm going to do the similar things by so far. This is quite the same as the what we have in the Gaussian Seidel method. I move the UX to the right. But now for the D, I'm going to use wave format there. I split it into two, and which means that I have 1 omega D and then minus 1 omega D plus L and then X minus equals to B minus UX. And for this part, I'm going to times both sides by omega. And I got D minus 1 omega D plus the L. And I should have, let me see, I should have, there's an omega here because I times both sides by omega. And I also have omega B vector here minus omega UX. And I'm going to move part of the D to the left, stay in, keep the one of the D to the on the left, and then move the other D expressions to the right. And at the end of the day, I decide to keep these two parts on the left and then move this part to the right. And I have this. D plus omega L and then X and then omega B. Let me see. And I also have minus omega U and plus the 1 minus omega D here, X. There's another X here. Okay, so let's solve the things. Solve this equation for X. And let the left-hand side just have, let the left-hand side to be X. And which means that we multiply the both sides by the D plus omega L inverse. And actually we have, I'm going to combine all the X together on the right hand side. And this part, it should be omega B. And I'm going to combine all the things. So which means that I'm going to use the plus sign here, 1 plus 1 omega D, and then minus omega D here, omega U here. And then these things, the result here times X. And this is just some game playing around the expressions we have here, split the A into the D plus L plus U, and then now we again split the D with two parts and then with the weight. And then we play the things around, move the things around, and then so for the X. And then we got this expression here. And now we let the left-hand side to be the K iterations result, and then let the right-hand side X to be the X minus 1 result. And we got to the relaxations method. So what is very important in the relaxation method is the omega, is the weight. We split the D into two parts, omega and 1 minus omega. So now the right hand side is the K iteration. Omega B here, and then plus the 1 minus omega D minus omega U, and the X K minus 1. And this is relaxation method. This is only relaxation. It's not the successive over relaxation, because over relaxation, and then it means something on the omega value. And so now let me just summarize all these things first. Let me see. So this one, we call because we want to write it into the general format, sk equals to the t and omega, which means that this is the SOR methods, the successive over relaxation methods. We are going to write it into this format, and then plus the C vector. T is the iteration matrix, and then C is the constant vector. And as you can see here, from the expressions above, and then we got the T omega equals to, it should be equals to the D plus omega L, and then inverse, and times the 1 minus omega D minus omega U. And this is the things. This is the matrix you have in the SOR methods. This is SOR method. And for the C vector, it's just the constant vector, and it equals to D plus L omega L inverse, and then times the, let me see, am I right? Times the omega and then B vector. Okay, where these two matrix vectors equals to this, and this is the SOR method. As you can see here, when you have, if I let this omega to be 1 here, and then this is just the left-hand side, we have the D plus L, right? And it's corresponding to the Gaussian cycle method. We don't have the 1 minus omega part. If we have omega equals to 1, so case 1, omega equals to 1, and that is Gauss-Seidel method. Gauss-Seidel method. And the case 2, when the omega is bigger than 1, and then we call it as the over relaxation methods. And when we have the case 3, and then there's omega smaller than 1, and then we call it under relaxation. And the name is not very important, but because we are going to focus on the over relaxation part, the omega, which is bigger than 1. So as you can see here, there are infinite possible omega here. You can choose any omega which is positive or negative, actually. But a lot of time people just use the positive number. The omega is positive number. So now the question is that if you have so many options, so many choice for the omega, and then T omega looks like this, and when does this methods converge for such an expressions here? So there is one necessary conditions for the omega value such that this methods converge. So this is necessary, not necessary, and it's not the sufficient condition. So if the things satisfy this condition, and then it does not saying that it's already convergence. So, but a necessary, which means that if it is convergence, and then it should have this values range. A necessary condition for convergence of the SOR method is that the number is in this range. It's in between 2 and 0, which means that people are not very people don't want to know anything above the omega bigger than 2, because when the omega is bigger than 2, and then the method is not convergence, and then people just focus their attentions on the omega which is between the 2 and 0. And in this class, we still we have a small range here. We focus on the omega, which is between 2 and 1, and that is the over relaxation method, and then the with convergence result. This is our focus of this class, convergence. This is our focus in this class, and then we just investigate the omega range here. Omega is between the 1 and 2. Let's see, the next part is to write down something. That would not be very interesting. Okay, so the next part is to write down the component wise. This is the matrix part. The matrix part, it looks like this, and actually you have a component wise expressions for the updating rule, and I'm going to write down that, and then but I'm not going to write down the details how to get the component wise formula for the SOR methods. SOR methods. So this one is the relaxations. This is the SOR methods, but the this one is the SOR method matrix format. SOR method matrix format. And this time we have the SOR methods, but this the component-wise format. Component-wise format. Let's see. So for each iteration, for k equals to 0 and then 1, let me see, shall I you see 1 here. Let us just start with 1. 1, 2, 3, because this should be the same as the things we have here. On the left hand side, we want the index to be k, and then on the right hand side, we want the things to be on the iterations k minus 1. So let's go back to here. The component-wise expressions, it should be xi, and then on the left hand side, we are calculating the k iterations component. The I component for the k iterations vector, and it's computed by AII xi k minus 1. That is the previous step result, and minus the omega sigma sum j equals to 1, I minus 1, aij xj. This is the current step result. You will see it's pretty similar to what we have in the Gaussian-Seidel methods. But we have the weight here, and then we also have the AII item there. This should be the k minus 1, the previous one, xk, xj, and then k minus 1 divided by the AII. And this is the updating rule. But if you compare to what you have in the Gaussian-Seidel methods, you will figure out that we have some extra term here, and then we have the AI term, xi term in these expressions compared to the Gaussian-Seidel methods. And we also have the omega here in the expression. This is the weight parameter, and you should choose a weight parameter here wisely if you want a better convergence result. But usually in your exercise, and then the omega is given. So let me see. Let's see. So this is I, and then it's from 1, 2, and then to n, which means that you need to compute n components for the for that example. So let's see one concrete example here, and that's the example. And we are solving. So the linear system x equals to b given by the following linear system: 4x1 plus the 3x2 equals to 24. 3x1 plus the 4x2 minus x3 equals to 30. Negative 2 x2 plus the 4x3 equals to negative 24. And actually, you can solve this with the Wolfram or Python, and then you would get the, it's actually has the exact solution. Three, 4, negative 5. But let's perform the SOR method with the omega equals to 1.25. It's between the range 2 and 1. And it's okay. And we can say this method is convergent because it's below the 2 value. And using the initial sweater, which is, we have the 3 system here. So we have the 3 component here. Okay. And actually I need the initial sweater in the question, and then it should be starting from the 111. And let's see the SOR methods. This is not very good because we need to calculate a lot of number here. Okay, let's see. Let's just use the numbers here to calculate the things. S1. So on the left hand side, we have, I'm going to copy their formula here. You can do some copy and paste as well. And I am going to copy it for 3 times because we have 3 components here. And the first one, I'm going to change it to 111. Oops. So for the first one, and then it's just x1. And A11. And this one is also 1. And j equals to 1, and then to the, because now the I equals to 1. So this one should be j equals to 1 to 0. What's happening? We will see later. What's happening here? Okay, so I equals to 1, A1j. J equals to 1 to the n is equals to 3 because we have a 3 by 3 matrix here. And then I equals to 1, A1j, and then B1 here. Okay, good. And now what about the second equation? Second equation, we just change the I to the 2. 2. Oh, this one is 1, 1. 1, 1. This one is 2, 2. And this one is also 2. So this is component-wise calculation here. And then this is I minus 1, I minus 1, I equals 2 now. So this one is 1, just 1. And here, this is AI2, I equals 2, and then A2J. And this is also A2J. I guess there's something wrong here. The very first equation, the J does not starting from 1 for the second equation. It's starting from J equals to I. J equals to I. Here, the J equals to I is just J equals to 1 because the I equals to 1 here for the first equation. But the second one, this one is should be also starting from J equals to I, but the I equals to 2 for these expressions. And we also have B2 here. B2. And let's see the third component. The third component, we change the I to B3. And also we have A3, 3, X3. A3, 3 here. And then also we have AIJ. I equals to 3. And 3 here. 3 minus 1 is just 2. And we have this one, it should be j from equals to I. J equals to I. And let me see. So it should be starting from 3. And then what's the n? N equals to 3. N equals to 3. And this one, aij, and then it should be a3j. And this one is ab3. Okay, good. We just changed all the index here, but there's nothing about the equations. We need to substitute the value into this equation, right? So let's do the concrete job, the detail job here, the detail substitution here. Oh. Let me move the things down. And what's the A11? A11 is just this is the A11. And it's just a 4. So I got 4x1 k minus 1. And then divided by A11. Am I right here? Let me guess. Divided by AII. So this one is 4 as well. Minus the 1 minus 25 because omega equals to 1.25. And as you can see, this is very confusing, the first one. J equals 1 and then you sum up to the 0, which means that we don't have any items in the first part. Can you see that? This one is not valid, this one. So let's skip writing anything about it. So we only have things from here. And also the minus b1 here. So what we have here, it should be a1j xj. So j equals to 1 first. So I have a11 x1 k minus 1 and plus the a12 x2 k minus 1 and a13 xj x3 k minus 1 and also minus b1. And I'm going to replace all the value here. Maybe you already get sleepy, and then when you get sleepy and then wake up and then you will see all the number change and then you don't know where it is from. I know this is mathematics class, get sleepy and then wake up and then you don't know where you are. And so now what is the A11? You have A11 equals to 4 and the A12 is just this expressions is 3. And A13 is just, A13, we don't have anything, and then which means that we have 0 here. And it's just 0. A13 is 0, it's just 0. And then what is the B1 here? B1 is 24. So I'm going to replace this one with 24. So at the end, what do we have is, you will see we are doing some subtraction here. This one, 4, and then minus the 1.25, and then times 4 for the first item. So at the end of the day, what's the coefficient for the x1 k minus 1? It should be, where's my pen? God stupid. Where's my Apple Pencil? I just put it down. Slip it into here, sorry. Oh, God stupid. Okay. Minus 0.5, 2.5 x1 k minus 1. And here the second one, it should be the subtraction is 1.25 and then plus 3 divided by 4, and then that is the coefficient for the x2 on the right hand side. So we have minus, this is by calculator, 375 x2 k minus 1 and for the third item, it's just 0. So we skip it. And so for the fourth item, that is the subtraction 24 times the 1.25 divided by 4. So at the end, you get this number by the calculator is the 7.5. You actually see how I do the calculation here, right? I do the substitution. And also you need to be very careful that you have the omega here, and then the omega is given by the question statement, and then omega is 1.25 here. And I just list one concrete detailed calculation here because this one is tricky. The superscript, the upper bound here is 0, and then some people just don't know what to do with this one. Which means that we don't have any items from these expressions. And for the rest of the expressions, I believe that you know how to write down their extensions here, right? Write down the expression and then replace the number A2J, A3J, finding the corresponding number, look for the corresponding number from the linear system of the equation, and then replace it to the expressions here. And then we got to the number, the expressions, and I'm going to skip the writing all the details here, and then you can take a look at the lecture notes, how the computations looks like. And this is at the end of this stuff. So I'm not going to talk more about this method, but you can definitely go back to take a look at the textbook, because I have the necessary conditions for the convergence result. Yes, we can choose the omega between 1 and 2, and it's over relaxation, and then it's convergent. But let's go back to our original goal. The original goal is to choose the T matrix such that, so the T matrix, it looks like this for the over relaxations method. And this is the T matrix. And if you look at the textbook, and then it gives you the result how to optimize this omega value, such that the spectral radius of the T omega can be as small as possible. I'm going to skip this part, to choose the omega to be the optimization's value, because you can see if you calculate the spectral radius of this part, it's very lengthy. So I'm going to skip this part, but I tell you that the idea is that, okay, you have this expression, and then we calculate the spectral radius of it, and then you will get an expressions of omega, and then you can do the minimizations over the omega variable, and then you will get the optimized value of omega, and that is the best SOR methods you get. You choose the parameter to let the matrix looks good. I skip this part. The things you only need to know is that example, how to write out the expressions. But how to choose the omega, you can take a look at the textbook, and the calculation is very lengthy, and it takes time to understand it. And that's all the things we want to talk about today. And then next time, I'm going to finish also discuss something on the linear system of the equation, but with the conjugate gradient method. And this would be on your exam as well, because you choose the first option. Good. I'm going to let you go. And if you have questions, please come over here. I could answer your questions. Go, bye-bye. This is Wednesday, and it's almost Friday.
Thank you.
Bye.